Welcome, everyone. My name is Gabriel Ocasa, and I'm a postdoctoral researcher at the Chair for Technology Innovation Strategy at the EPFL. And today I would like to introduce you the idea of meta-learners for estimation of causal effects. And in particular, I would like to show you some finite sample CrossFit performance. And so what is the research question in this project about? We are interested in the finite sample performance of machine learning-based meta-learners using cross-fitting for estimation of heterogeneous causal effects. So this might sound a little bit complicated, so let's break this down a little bit. So why do we care about the meta-learners, or what are these meta-learners? So these are basically very generic procedures or very generic estimators that decompose the estimation of the causal effect into estimation of a separate prediction functions. And then you can choose any supervised learning method to estimate these prediction functions and combine the predictions to estimate the heterogeneous causal effect. On the other hand, the cross-fitting is a particular procedure how you can implement these meta-learners. So it is about the data usage, and cross-fitting basically combines the ideas of sample splitting to reduce the bias, but adds also another bit to regain the efficiency to use all the available information in the data. And so in this paper, we want to have a look at the simulation evidence for assessment of these meta-learners together with these estimation procedures. So very shortly, we are interested in the binary treatment settings, where we are interested in estimating the nuisance functions for the propensity score and for the conditional expectation of the outcome. And then the meta-learning part combines these data inputs with the estimated nuisance functions to estimate the treatment effect. And so to have a little bit more graphical view of this is to basically, you can choose from three options. Either you estimate both of those nuisance functions and the treatment effect on the same data, which we see on the left, or you split the data such that you estimate each of these functions on the same part of the data. And the cross-fitting just combines these procedures such that you do not waste any information available in your sample. And so to give you a little bit more idea how this actually plays out in practice, what you can see here are basically three distributions of the treatment effect simulated, where on the left side you see the full sample implementation, in the middle the sample splitting, on the right the cross-fitting. And what you can see here is that basically for the very same estimator, we can achieve a very different result just based on what kind of estimation procedure we choose from. And so in this framework, we want to evaluate this in the set of simulation studies. And in particular, we have a look at the empirical convergence performance of these meta-learners, or how these meta-learners behave when we increase the sample size. And so the results basically show that the ideas of sample splitting really effectively reduce the bias when we have large samples at hand. And cross-fitting additionally regains the full sample size efficiency such that we do not waste any information available in our data. However, in smaller samples, the full sample estimation is preferable when using machine learning. In respect for the meta-learners as such, we see that there's really a lot of variation in the impact of these estimation procedures. So we can identify some meta-learners that are very robust to which of these procedures you choose to estimate the treatment effect. And on the other hand, we see that some meta-learners are very sensitive to these procedures and are really performing best in combining the cross-fitting ideas in large samples. And so the basic takeaway of this paper is that the performance of these meta-learners really varies greatly, but the choice of the meta-learner and the estimation procedure can be actually guided by observable data characteristics such as the treatment shares or the sample size, such that the applied researcher can really assess the particular empirical setting at hand. And with that, I would like to just conclude and thank you for your attention. And I will be glad to discuss more in detail in the breakout room. Looking forward to it, and thanks again for your attention.